Ever wonder what happens when things go wrong and you need to recover data in ZFS? Or if you have a lot of snapshots, does that lead to performance issues? Well, to answer those questions and many more around data integrity, I had a great discussion with Allan Jude from Klara Systems. We also talked about the future work being done to enhance ZFS MVE performance, container management, and a lot more, especially some interesting discussion around deduplication. And despite all of you that leave comments otherwise, Allan Jude confirms that ZFS is really a cow or copy on write file system. So let's get started. Welcome, Allan Jude. Great to have you here. I've been a longtime fan of like the two and a half admins podcast, and of course the all the write-ups at Klara Systems and things like that. So we're here to talk about some ZFS horror stories and just some general ZFS stuff too.
Yeah, thank you for having me on.
Yeah, I want to start out with some of the work you and Klara had contributed to. I love ZFS Expansion. That is, we were so excited. I also, because I've talked about it, I remember when it was announced that there was a lot of work going into it. And of course, there's a long time and people are like, well, when's it coming? When's it coming? But something I appreciate so much, and you could probably speak to more here, I don't mind that it took a long time because I have a lot of data on ZFS, and I don't mind that we did things very carefully and very thoughtfully on how to do it. Storage may be a bit slow and implementation of things, but it's all that quality checking that goes into it.
Yeah, there's always a tension and a trade-off between, making sure that every new feature gets enough review and enough testing and, worked on very consistently and methodically before it goes in. And even then, once it goes into the master branch, we expect a lot more testing and wider use that will catch the things that an automated test wouldn't. But before it goes out into a release. And that's one of the things Klara is working on for the future is being able to make that easier. Like right now, if you want to use kind of the developmental branch of ZFS, especially in a test VM or something, not necessarily on your production systems, you kind of have to follow the developer instructions and kind of like download the source code and build it yourself and deal with all the issues. Whereas one of the ideas we have, especially for test environments and so on, is to maybe have a pre-built Ubuntu package of the OpenZFS master branch, so that you can basically easily install the beta version of ZFS and test it. And we hope that will get more people testing out new features and finding issues so they can be fixed before releases happen.
That
In
would be
addition
pretty
to all the
cool.
automated testing.
Yeah, that would be pretty cool because I admit myself that it is not easy, as I understand it, to get going on that. So I
Mhm.
don't do as much the same way. I do like testing beta software because I have enough extra servers that I'm always experimenting with. But making it easier, like in Ubuntu, to say, hey, let's go ahead and with the unstable branch, so I can test out the new feature and do some edge case that you go, why would anyone do that? But you're right, we should probably not have that. We should probably address that particular edge case.
Yeah, there's been a lot of interesting stuff happening with the block reference tree, the file cloning feature that allows you to basically make a copy of a file without the cost of dedupe, but without actually taking twice as much space, which can be really powerful for workloads like VMs and things like that. Uh, and now we're starting to see people using it for backups to basically have multiple kind of synthetic full backups by cloning the parts of the file that didn't change. So it doesn't take any more space, but each backup is the whole backup. Kind of getting the same advantage you get from snapshots, but when copying it from another system. Uh,
Oh,
and that's really useful, but it's a different set of scaling problems than BRT was originally designed for.
Deduplication is great until you really think about how it works. And I understand, and the fast dedupe work is cool. There's definitely been some improvements, and I want to eventually I'm going to do a video showing some of the use cases for it because it's not the solution to automatically dedupe everything because there's some costs, as you say, for scaling for
Mhm.
doing it. But there are use cases, and this sounds like a really interesting one where that would be pretty effective.
Yeah, and fast dedupe goes a long way to making dedupe not have a performance curve that goes down and down and down as you scale it up. And fast dedupe solves a lot of that. And the thought is to look at some similar concepts of basically instead of updating the table each transaction group, we kind of log the changes and then deal with them in a batch. And that's how fast dedupe works. And looking at maybe doing the same thing for BRT so that when you're cloning terabytes and terabytes of backups, that the performance will be, much more what people expect, and how well block cloning works when you're using it for, moving files between data sets or restoring things from snapshots, and the original use cases that BRT was designed for.
I think it's interesting in the rise of ransomware and people going, what magic could we possibly invent to try to recover from this fastly? And then they go, wait, someone invented it. It's called ZFS. If you store it there, we've got a lot of clients using that, and there's all those things. The same thing with the synthetic fulls and some of the more work just going on there. ZFS has got some pretty amazing tool sets for doing this, and it's been around for forever, being iterated on. It's one of those things that I'm always impressed when I think about ZFS of it's so written long ago, but still being used so many years later, partly just because of the vision it took to build out the architecture for the first version of it to where we are today. Not to say it's not dramatically had to be improved by many people, as aforementioned, the
Mhm.
the fast dedupe we have now versus that wasn't there before, and of course the RAIDZ expansion, which makes life much easier. But one of the things I want to quickly address is something we mentioned it because it was just one of those like people who want to deny that the Earth is round moments. There seems to be this weird amount of people that tell me ZFS is not actually a copy on write file system. I think you can validate that it is, right?
It definitely is. And so to kind of explain the concept, like in general, yes, copy on write means that when you change a file in ZFS, instead of overwriting that file in the place where it already was on disk, if a chunk of a file changes, ZFS will write the new chunk somewhere else and then update the metadata to say, chunk 7 of that file is now in this other location on the disk instead of where it was before. And then even the metadata block that points at, we actually make a copy of that, so that we have the old one and the new one, and all the way up the tree. And so changing one block on the disk can actually change like 7 or 8 blocks in total elsewhere in the tree that eventually leads you to that block. Um, and the reason we do this is if you take a normal like NTFS file system that overwrites in place, or ext4 or whatever, if you're in the middle of writing out a file, like if you have a document open and you make a bunch of changes and you hit save, it's going to overwrite the file in place. It'll overwrite the entire file. But if the power goes out, say halfway through writing out that file, then what you're going to have is the first half of the file will be updated. It'll be the new size or the new data. But the second half of that file will not be. It'll still be the old copy. And that's what we call a shorn write, where we were halfway through doing it and we got cut off. And that means now that file is basically corrupt, right? Like your document editor,
Yeah.
like unless it's plain text, your editor's not going to be able to open it, right? Like most documents are compressed and other things. And so that stream is just going to be, it gets halfway through it and then the rest is garbage. Um, and that means that file's now corrupt and you don't have either copy of the file, right? You don't have the old one or the new one. You have nothing. Whereas with ZFS, because it's copy on write and all the way up or down, whatever way you want to say, that means that if we were in the middle of doing that, if we wrote the new copy of the file, if we only wrote half of it, then we never updated any of the pointers. And it doesn't matter. When we bring it back up, we'll have the unmodified original version of the file and we'll be okay. Even if it does finish all updating the file but it doesn't finish updating the metadata, then again, when it goes to load, it'll see that the metadata still points to the old copy. Or even if we go all the way up and have updated all the metadata, when ZFS imports the pool as part of mounting the file system at boot up, it checksums all those blocks. If any of those checksums fail because something didn't finish, right, we wrote it to the disk, but it was still in the cache and the disk didn't have power loss protection and it didn't finish writing it out before the power went out, then ZFS can just automatically go back like 4 seconds to the previous transaction group where that file was perfect and boot up and give you that. And this way, basically, you don't need something like fsck or whatever to recover after a crash because ZFS moved from everything is perfect to everything is perfect and one version newer. And it just takes one step at a time like that.
It it's one of the reasons that there's so much complexity in the writing of it and why there's things like these SLOG exist and stuff like that to help manage those transactions to make sure they're committed. But there's some brilliance when I've read through papers on it and tried to really wrap my head around it as I was learning ZFS. I'm like, wow, it's a lot, but then it makes sense because this is all that integrity checking in there.
Yeah, and it's why people often wonder, why does ZFS seem to be a little bit slower than other file systems? It's like it's kind of a miracle that it's not a lot slower because, in ext4, if you're overwriting a file in place, you're writing those blocks and maybe updating the metadata to have a newer last modified time. In ZFS, you're having to update that block, its parent, and maybe 3 or 4 levels of parents, depending on the size of the file, and then all the stuff all the way back up to the root of the file system. ZFS does a lot to try to amortize that cost by basically combining all the changes you made in 5 seconds and writing that out all at once to avoid rewriting, that same block, having to copy and write it like 12 times over the course of 5 seconds, by just keeping it in memory and doing it only when you ask. And like you said, the SLOG, the separate intent log device, is if you're a pool of mostly hard drives where flushing stuff out and saying, hey, hard drive, I've written that and I'm asking for a guarantee that you've gone all the way through your cache and it's actually on the platter and it'll still be there if the power goes out. And when you ask for that, the hard drive, it can take like up to 20 milliseconds to actually finish all the what it has to do to guarantee that data will be there after the power comes back or if the power goes away. And so that cost is really expensive. But if we have, just one SSD as a slog, then we can say, all right, you've asked for this one little file to be persisted. We'll write it to the slog now and be able to say, yes, it'll survive a reboot very quickly in like 1 millisecond. And then as part of the big batch we do every 5 seconds, we'll write it out to the hard drive. And once it's there, we can mark the copy on the SSD as just, we don't need that anymore. But if the power goes out in the meantime, we have that copy on the SSD to replay and get back to the state we're supposed to be.
And I think that's where some real confusion can come in. I believe the term is intent log is what's being written there, but it's actually just holding in memory. There's a copy in memory and there's a copy on the intent log, and it's streaming it to the drive during that 5-second transaction group write. And it's just not really doing anything because people get concerned because like, I need to buy a 2 terabyte slog, right? No, it's not a write cache, and 2 terabyte consumer drive is probably not ideal. A really small drive with high queue depth is probably a better ideal that can do the commits. If you can speak to that a little.
Yeah, usually a larger size drive sometimes is better because it has more write endurance, but
Yeah.
you're never going to be using more than like tens of gigabytes on it because it's never really going to hold more than 10 seconds worth of data. Because as you said, you're doing your workload. It will be a mix of what are called asynchronous writes, which is just, I copied a file or whatever, is just we asked ZFS to write it and we said, we don't care when it's done. I wrote the data, I give it to you. It's not my problem. I'm out of here. And then for things more like databases, they'll do a write and say, okay, now tell me once that is going to survive the reboot, and only then will I complete the step in the database because the next change is going to rely on this change, so I want to make sure it's there before I move on. Or if it was somebody placing an order for something online, we want to make sure that it's going to survive a reboot before we give them the page, thanks for your order. And so when those happen, we can basically write a second copy of them to the slog. We still write the normal way, as if nobody had asked for a promise. We still keep it in memory and write it out every 5 seconds. We've just written this extra copy in case the power goes out. And so whatever you write to the slog, short of the system crashing, you never read that data ever. You just write it, and then if the time goes by and we wrote it out normally, we can just forget it, and we just run over it over and over again. It's basically just a bunch of pre-allocated space to stave stuff in case the power goes out.
Yeah. And that's why I say if you turn off the sync, right, in a home environment, you're fine. But if you're in a database environment, you really want those committed rights. You want to validate they're committed. And especially if you're in the financial institution, I want to know that my banking transaction has occurred, that the money transfer went through. So when you talk about anything that really absolutely requires integrity, ZFS is fine to use, but you always make sure you have synchronous writes. But those have that performance cost that you want to make sure you get some fast drives or a really fast pair. I would still recommend, I think it's still recommended that you at least have a pair of the
Yes, the
slugs.
slug, you usually do want at least a mirror because if it dies, then you don't have that data that you need to replay if the system crashes. And especially, drives dying is one of the types of things that often causes things to crash.
Yeah.
ZFS does very good about that, but it's limited by what the operating system and the hardware are willing to do.
Yeah. And suddenly a drive just decided it's time to give up the ghost. And I feel like, sometimes when there's some noises that with spinning drives that you're like, okay, this might be a problem. I feel like they don't fail often, but they always seem to fail immediately and catastrophically when it comes to the solid state ones. They work and then they don't. It's been a lot of
Yeah,
my experience with them.
it's interesting in that a lot of devices, if they would just fail, that'd be nice. But oftentimes they kind of limp along with like a broken leg kind of thing. They're still working, but taking a really long time to do stuff, or otherwise causing a problem. Like especially you can get if you're using SATA drives over a SAS bus, then when the SATA drive's having errors, it was described to me as someone shouting and bleeding from their eyes in a room full of people. It's like all the other people can't really continue their conversations while this is happening.
Yeah.
And so it can really drag things down. And so it was one of the features that we're in the process of upstreaming to the next version of OpenZFS is a mechanism for RAIDZ. When you have an array that's like 6 wide or 10 wide or 12 wide of drives in a RAIDZ, if one of those is going slow, it basically drags the entire VDEV down, right? Because if you take 128K chunk and write it out across 8 disks, when you want to read it back, you have to read from all the disks. And if one of them is being slow, then you don't finish that read until every one of the 8 drives is finished. So we introduced a feature where ZFS kind of keeps track of the amount of time most reads are taking from each drive. And if one of those drives is taking a lot longer than all of its peers, then we decide, okay, we're going to put that drive on a 5-minute timeout to see if it catches up and is back to normal or if it's really failing. And during that time, we can just use the parity in order to reconstruct the data and still complete the reads quickly. And then it does it a couple times, and if it's the same drive keeps being the problem child, it can raise an event to the fault management tools and say, hey, maybe we should replace this drive with a spare because it's obviously on its way out, or something is wrong with this one drive.
Oh, that's really cool. I really like that. That is something. So I have an array now that it's not production, it's just backup, but it's annoying me because one of the drives is spitting errors. But I got to get back to where this thing is because it's off site and I got to drive out there and put a new drive in it. So I've been kind of ignoring it, but I know when there's a problem like that, it is annoying because, like you said, it just kind of pauses. So I really look forward to that feature.
Yeah, we've built arrays specifically for kind of like the situation you're talking about, where we had to build a 1 petabyte pool for a museum, and they were using it actively, and they wanted to basically have a real time replica of it offsite at their backup facility, which is like 3 states away. And so, they have to book a flight and go out there if they want to do maintenance on it. So it's like we can do maintenance on this once a quarter, once every 3 months, and that's it. So we had to design it with enough fault tolerance of a bunch of RAID Z3s and lots of spare drives and so on, so that this machine can go 3 or 4 months with no one being around to touch anything and to replace anything, and it still had to be able to operate and maintain that backup in case a hurricane or whatever got the
Yeah.
server wet, which is a nightmare scenario.
Question back to the transaction groups. I've never had to do this myself, but you deal with a lot more advanced things than I do. Has the 5 seconds? I believe that can be changed. And how often is there ever a need, actual need, not request? There's always requests, but there's an actual need to change it.
Usually not that often. So back in the early days of ZFS, the default was actually 30 seconds instead of
Oh,
5. But it was found that this could cause kind of a stutter effect where all these writes would build up. And in the meantime, this pool is mostly just focusing on reads. So part of the reason why the transaction group is set up like that is because, how the system feels is mostly about how long it takes to do a read, right? When you're trying to do stuff. Um, and then because, physical hard drive, you have the head seeking around. If you're mixing in the writes with the reads, it slows both down, right? Because it's twice as much seeking you're doing. So ZFS kind of says, all right, we'll do all the reads and then we'll pause for a second and do all the writes really quick and then go back to reading. But when we were accumulating 30 seconds of writes, uh, then the amount of time we paused to do writes could be, a whole second or more. And then if you're reading fine and then the performance drops for a second and then fine and drops for a second, it felt weird. So that's when the default was adjusted to 5 seconds, because unless you're writing as fast as you can, you're probably not going to accumulate a lot of writes every 5 seconds. And that 5 seconds is a maximum. So if it's been 5 seconds since the last time we flushed a transaction group, we'll do one. But There are other mechanisms ZFS, so it tracks, it has an amount of your memory that it will use to store up those not written out things yet, and that defaults to I think like 10 or 20% of your RAM, or 20% of the size of the arc, which is depending on your system, maybe half your RAM or whatever. Uh, if that gets 20% full, it starts the next transaction group. And then after it gets 60% full, it starts slowing down the application and saying, even though you didn't ask for us to wait, we're going to wait a couple milliseconds before we return to eventually try to slow down the incoming rate to match how fast the drives can actually write it out. But yeah, so while the maximum of 5 seconds, if your system's busy, it'll be doing it more than often than every 5 seconds in
Okay.
order to uh, not run out of memory trying to store just everything
Yeah.
you've written. If you're copying a 16 gigabyte file and you only have 8 gigs of RAM, we can't wait 5 seconds if you can read it that fast. But in general, yeah, the 5 seconds has been found to be really good. Um, for other use cases, we're actually experimenting with a patch now that allows you to specify that in milliseconds instead of seconds, so that it's possible to have a transaction time of less than 1 second if you want. Although so far we've seen that has quite a bit of cost. One of the advantages of waiting that 5 seconds is, you change something and that updates all the indirect blocks, and you change something and that the other set. If you make 10 changes, if they all change the top couple of blocks only 3 times, that's a lot less work. Whereas if we do it too soon, then we're overwriting the same block over and over and over again because of the changes, and so you're missing out on some of the performance gain you get by batching a bunch of changes together. So there is some cost to having it be too short.
With NVMe's and especially the commercial ones becoming so much less expensive, how's ZFS handling those? Pretty well, or is there been more innovation? Because if I have an array of NVMe's, what does my slog look like at that point? Because I got to go something generally faster, but I think we're reaching some pretty fast write speeds at that.
Yeah. We have seen tools with the NVDIMMs. So basically,
Yeah,
almost a stick of RAM that will survive a reboot, that is even lower latency and so on. Or, most of the time with an NVMe pool, we just don't have a slog. When
it's
you don't
fast.
have a slog, the ZIL, the ZFS intent log, is just embedded into the main devices. And, it's easy enough now to get NVMe devices that can do, a million IOPS of reads and, a quarter million IOPS of writes for even reasonable prices now.
Yeah,
So ZFS is getting there. There's more work to do because ZFS was designed for hard drives, especially around. It spends a lot of time doing things like I'm going to, sort all these and batch them together and try to aggregate these two small writes into one bigger one, because on a hard drive, that's faster,
yeah.
right? The fewer times we have to seek, the more performance we're going to get. And, a hard drive, the average time it takes to move to a different spot and write something is about 4 milliseconds, right? And that's where you get the 200 to 250 IOPS you get from a hard drive. And with an NVMe, you can be talking about hundreds or even tens of microseconds for each of these operations, right? To be able to do 100,000 of them per second, they have to be really, really fast. Uh, and so suddenly, the spending a bit of CPU time to try to optimize that before sending it to a device that's going to take at least 4 milliseconds to do it can make sense. But when the device can take, 50 microseconds to do it, maybe all the time we spent in the CPU is actually slowing us down. And so it's a bit looking at that. And the other big thing is ZFS spends a lot of work trying to keep the queue depth short on a hard drive, right? We want to, the more things we give the hard drive, the more it can sort them and be more efficient with its seeking. But if we're doing a bunch of writes or even reads that are asynchronous, like we're prefetching a file, right? You're reading a file, and we kind of ZFS will try to go ahead of you so that it's already in the cache by the time you do it, right? If you're reading 4K at a time, we can read the next 1 megabyte of the file and be able to give it to you faster. But we want to keep the queue of those short so that if something important comes up, right, if you're trying to read a different file and you need it right now, or you're trying to write something, and for example, you're writing something and you don't have a slog and you want the guarantee that this is going to be there after a reboot, you want that to be at the beginning of the line, not at the end of a really long queue before it gets done. And so ZFS tries to keep the queue to the device really short so that it can make sure that anything important gets to go to the head of the line. But with these NVMe devices, you need to basically really fill the queue, or rather, instead of one line that can have maybe 32 jobs like a SATA SSD or SATA hard drive, an NVMe has 63 or 64 queues that can each have 64 commands in it. And you kind of have to, if you look at the specs for like a Micron NVMe, they're like, yeah, to get the results that we show in our spec sheet, you have to have 256 queue depth spread over those 64 queues. And so you have to push it a lot harder. And so ZFS has to kind of work against the way it was designed in a few places to try to make sure it's keeping up with that and keeping those queues full and limiting how much work it has to do once a write completes uh, to queue up the next thing, because we want to make sure the latency like the amount of time the NVMe spends with nothing on its list of what to do as little as possible, because that's basically IOPS that are being wasted every microsecond that it doesn't have a list of things to do, then it's not doing those things.
In this question has come up quite a bit because people, they start, buying some of these and they go, wow, I'm not getting the performance I expected. And I'm like, well, it's not that ZFS doesn't support it. As you more elegantly described, it's not optimized for it very well until some more work is being done. It's really interesting just how, as I know you've been a long time in tech, crazy, because the first drives I ever set up are RLL MFM. Like the seek times are so slow compared to where we are. We're like, hold on, the CPU might be the bottleneck here.
Yeah. Or just, the amount of time it takes to give it the list of things to do. It'll be done them before you finish feeding it that list. And so if you then wait to get the list of completions before you feed it more, then, it spent a bunch of time idle. And that was performance that was left on the table. We've
Now,
definitely been able to get, 400,000, 500,000 IOPS out of ZFS. So it's not that it can't do a lot. It's
yeah,
just, it
could do
will
more.
not necessarily be the same as other things because it is doing so much more, including checksumming and the compression and all this other stuff. Uh, and oftentimes you can actually run into the limit of the memory bandwidth of your motherboard, and how many of it, like having not necessarily more RAM, but more sticks of RAM. So using more of the channels on like the newer AMD CPUs, uh, in order to get more of that bandwidth to be able to uh, move the data around in the CPU fast enough.
Yeah, there's some interesting challenges that come with it because we're hitting some of these limitations. Same thing when I was helping someone build out a server that's got a whole lot of graphics cards in it for processing, and you run out of lanes. Like
Yep.
we want to put this many graphics card in. Okay, you're going to have to choose something that has enough lanes for it, and that's the same reason I'm starting to see some NAS companies make some boards that have a bunch of NVMe slots for the consumer ones, but that's the consumer ones are different than the ones like from Micron or Kioxia,
Yep.
those companies that make the commercial ones, because they just don't have the queue depth. So people kind of do the math on the back of the napkin math going, well, I seen what consumer told me this little stick of gum style thing will perform at. So if I multiply that times how many I put in, that's my throughput, right? And not just because of ZFS optimizations, but also because of the way the queue depth matches on those. You have some horror stories where people maybe chose the wrong ones, and then they always, people reach out to you afterwards, where the horror stories come from, because you didn't design it. They're like, I bought a bunch of the wrong thing. Can you make it do the right thing?
Yeah, I think the biggest one we saw of that was a company who had bought some really low endurance SSDs as their slog. And they were running an actual database handling transactions. And so they were writing to the slog a lot. And eventually the slog ran out of write endurance and switched to being read only. So instead of failing, it switched to being read only, which is somewhat helpful. But ZFS really doesn't expect to just continuously get write errors from the slog. That wasn't something that had really been widely tested, because it was kind of an odd case, right? The slog failing it can deal with, but the slog reverting to being read only was an interesting case. Uh, and yeah, it's like interesting. It's like all the SSD you could buy, and you somehow bought the worst possible SSD to use as your slog, as one of these really low endurance, like quad level cell ones that just ran out of life after a year.
Yeah, and people really need to look at how the different models work. Like they just see,
Mhm.
oh, quad level makes it better. Not necessarily.
Yeah, it'll have much less endurance, and it'll be bigger for less money, but it won't be as fast and it won't last as long, or it won't it'll wear out sooner. And there's been a lot of talk about how a lot of times people are biasing too much towards worrying about their SSDs wearing out, when most of the time, any reasonable workload is not going to be able to wear out the device. Like the I think 7.68 terabyte NVMe's we were looking at, you can write 14 petabytes to it before it'll start to wear out. That's quite a bit. But especially on the consumer side, some of those are really low endurance, or especially, we've seen companies selling these 120 terabyte devices. Most of the newer ones are actually, really solid SSDs that have been scaled up. But some of the early ones from like 2 years ago that were over 100 terabytes were like really low endurance. Like you could write to them only 1,000 times and that was it. And for some workloads, that makes sense, right? If you're writing the data once and you're just going to read it over and over and over again, then that drive will work perfectly fine for that. But if it's your slog and you're going to be writing and flushing to it, hundreds or thousands of times a second, it is going to wear out eventually. And especially the other thing we're seeing there is, in order to make these larger capacity NVMe devices inexpensive, they want to change the sector size. So basically, in most of these NVMe's, there's actually RAM that's holding the flash translation layer table. So this is the one that basically takes, a hard drive style like sector number, that this data is at this specific place, and allows that to translate to where it actually is in the flash, so the SSD can move it around under the hood to do wear leveling and to, that flash cell's gone bad, we've copied the data over here instead, and all that kind of stuff. So it allows, it provides indirection so the NVMe can move stuff around under the hood to wear out the flash evenly and deal with wearing out flash and so on. But in order to be fast, it has to keep that table in RAM when it's running, right? It has a persistent copy as well, but it really needs to keep that table in RAM as running. And so that's why we saw, especially NVMe's kind of pushing to, 4K sector size instead of 512 bytes, because that means each entry, you need 8 times fewer entries or more to not, you need less RAM that way.
Yeah.
And so with newer NVMe, we are seeing them going up to like 16K or 32K or even 64K sector sizes, because every time you double the sector size, you half the amount of DRAM you have to install in these devices. And if it's going to be a 62 terabyte NVMe, that's a lot of RAM to map out every 4K sector separately. Whereas if you make them 16K sectors, you need 8 times less RAM. And the thing is, a lot of
Trade-off.
applications, there's a lot of trade-off with, your read, modify, write things, and just the way every file system, like most file systems were really not designed to handle these sector sizes. And so, the firmware emulates the smaller sector and does it under the hood for you, but it can cause really weird performance things when, I wrote 4K, but the NVMe had to read 64K, modify the middle 4K of it, and write 64K. And so even if the device can write 8 gigabytes a second, if every write is being multiplied by 8, now it can only really write 1 gig a second if it's not all aligned to the sector sizes.
Yeah, and if you're streaming large amounts of data and I'm sending a video to it, sure, it can chunk that up. But if back to our transactional databases doing small, tiny kilobits of writes, that's going to have a massive performance impact on that.
Yeah, and we had a really interesting case where this happening. It was a hard drive based pool, but they were using a little known feature of ZFS called the no-op write, which is when you write data, or when you're overwriting data in place in ZFS, when it calculates the checksum, if the checksum matches the checksum of the data that's already on disk, ZFS knows that it doesn't actually need to do the write. So it can just make it a no-op and not actually do the extra work. This was invented because I think Oracle databases tend to, during their refresh operation, actually overwrite the data in place.
Oh, okay.
And if most of the data hasn't changed and you can avoid doing all those writes, you can make it a lot faster. It's a nice optimization. So this customer of ours was using this feature as part of a backup mechanism where they would basically take an image of the whole hard drive of a machine, and they wrote it out. And then later they'd take another image of it and write it over top. and know that ZFS would only write out the changes of what actually changed. So even their snapshot would be smaller because it would only contain the differences. And that was great, except for they were doing it over NFS.
Oh,
And so while their ZFS had the default record size of 128K, the NFS in the middle was breaking the writes up into 64K chunks. In order to do this, what ended up happening is we'd write the first 64K of a 128K chunk. And because it was a sub block update, ZFS had to read the whole 128K, have that in memory, then overwrite the first 64K of it with the new data, then calculate the checksum, see that the checksum is the same, and then say, okay, we don't have to do this. But they had caching turned off on purpose to not, they because they knew they were just going to be writing this file over and over again, not reading it, they were disabling the cache so that ZFS wouldn't use the RAM for that. And it would keep the cache for the other data sets. So now the second 64K of that first 128K block comes in over NFS. And so ZFS has to read the whole 128K again, even though it had just done that read. Because the cache is off, it had thrown that copy away and had to read it again, and then rewrite the second 64K of that block, calculate the checksum, find out it was fine, and throw it away.
oh,
So in the end, they were reading the block twice, calculating the checksum 3 times, once after the read to make sure it was right, and then once for each half of the update, and doing all that work, and then deciding there was no work to do. So when they fixed NFS to be 128K or adjusted ZFS to use a matching record size of 64K and rewrote the image, now they would do 64K right. We would see the checksums the same and do nothing. So now we did 0 reads, 0 writes, and 1 checksum calculation instead of 2 reads, 3 checksums, and 0 writes. And suddenly it was much, much, much faster.
those sector alignments and little details like that,
Yeah.
let's set some block sizes to match. That's when you're using any of these, there's that whole chain of events you have to look at, not just the ZFS. Because people
Mhm.
always ask, like, what's the best settings for ZFS? I'm like, well, what's your workload? And how are you transporting that workload? Is it iSCSI as a ZVol on a block device? Is it NFS? And then back to the sector counts and back to what is it even writing?
Yeah, and what is the application? And that's one of the powerful things of ZFS is with the idea of datasets, these kind of virtual file systems that share the pool of free space, is each one can be tuned differently. So it makes it possible, like there's no one best setting, but you can tune ZFS to do the right thing for your database in this data set, the right thing for your video collection in this other data set, and the right thing for this imaging software or whatever in a different data set. And yes, a lot of the work we do at Klara is helping companies like, we have one company who's doing color correction for like Hollywood movies. And so they have this big storage machine of all NVMe's, and then they have 4 editing bays and these really, really expensive editing machines. And they needed to be able to pull in the video files at no less than 1.1 gigabytes per second each, because it was like 8K videos. So each individual frame is like an 80 megabyte file. And they have to be able to pull back those at like 24 frames a second. And so they had to make sure the performance would never drop below that. They had to, however much over it didn't really matter, but it could never, ever go
Because the
below
video
that
would
number.
stutter.
Yeah, because the video would stutter while they're trying to do this color correction editing. And so, designing a system that can handle 4 of those happening at once and making sure that we would never drop below this minimum performance meant a lot of benchmarking of like the worst possible cases, like not just reading these nice big files contiguously, but like make sure it can handle that performance when we're reading all over the place and other things are happening and a scrub is going on, and everything we could do to make sure that it will always meet that requirement.
Now, in that type of scenario, did you go with a bunch of mirrors or did you build out a bunch of VDEVs for the performance?
They did many mirrors, so they have lots of VDEVs to spread it across. And you know, in this case, they were willing to spend the extra. These were expensive NVMe drives, but getting only 50% storage efficiency was worth it to be able to make sure they could basically saturate their 100 gigabit NIC. Well, not saturate it because that would randomly cause latency and that'd be bad. But that they could keep these 4 editing bays fed when they're all being used at once.
Because that's a debate that comes up a lot is people always, I've done talks about the layouts and efficiencies of it, and I don't push unless there's some really demanding performance because of the storage efficiency loss of mirrors. Mirrors are fine. There's nothing risky about doing a mirror, but it is certainly a challenge because you have to have a budget that can support it, and enough bays to put all the drives in, usually to reach the capacity you're looking for.
Yeah, for a company that did more backup type workload for their big VM cluster, we built a machine for them that had 200 mirrors of, I think, 12 terabyte hard drives. So that was like 400 drives spread across like 4 of these Western Digital chassis, all plugged into the one machine, uh, because they needed that much capacity, but they still needed enough IOPS. Whereas if they'd done RAIDZs, if you do a 12 wide RAIDZ, you get the IOPS of basically one drive from all 12 drives. Whereas if you did that as mirrors, you would get at least 6 times the speed of one drive instead of 1 times.
Yeah, that's one of the challenges, though.
Yeah,
Certainly,
and
it comes
obviously
down to
with
really planning.
mirrors, with mirrors, you can get all the apps on reads. It's just on writes you only get half. But
Right.
most workloads are a mix of reads and writes, and so you never get double, but maybe you can get a bit more than 50%.
Yeah. So know thy workload. Question on a little bit of recovery here. So snapshots are amazing and brilliant and one of the favorite things in ZFS, but sometimes people don't have snapshots. And what I
A lot of
frequently
times.
get, and I've just say call Klara because that's beyond my control to help you. They have deleted things off the drive, and what's the likelihood, depending on what scenarios, that you can recover accidental deletions, but we have no snapshots to revert back to from ZFS?
It mostly depends how long has it been. Uh, in general, as we talked about at the beginning, when we're doing this copy on write thing, the very, very, very top of this tree is called the Uber block. And ZFS keeps a ring of those. And so with a 4K sector drive, there are 32 Uber blocks in the ring. And so the last 32 transaction groups you can rewind to. And sometimes you can go further if you have a mini VDEV pool. We don't overwrite every Uber block on every drive every time. So we keep a slightly larger array. And we've used that to be able to go back and get the pool in a state it was a couple of transactions ago. Although most of the times that we've done this have been more problems with HA systems. Like there was one university where their HA system went haywire and both the primary and backup server imported the same shared set of disks at the same time and were overwriting each other. But they caught it before there had been too many transaction groups, and we were able to kind of rewind and have very limited damage. We got back like 99.7% of the data
Oh, that's
by
much
being
more
able
than I
to kind of
expected.
go back in time using those transaction groups. And really, what a snapshot is in ZFS is just a specific transaction group time, and we say that any blocks in this data set that were born before the snapshot can't be deleted until the snapshot goes away. So ZFS doesn't have to keep a list of every block that's in a snapshot or anything. It just every block knows what the transaction group number when it was created or modified. And the snapshot just says, when I exist, anything older than that is part of the snapshot. And so if you overwrite it, so normally with copy on write, you have your block and you change it, you write a new copy over here and you update the metadata, and the old copy gets marked as free space. If there's a snapshot, we just skip that step for now and don't mark it as free space and put it on a list in the snapshot and say, when you delete the snapshot, that one can become free now. And so the snapshot just keeps us from overwriting the old copy of the data so we still have it. And by default, ZFS won't overwrite it right away. It'll wait a while.
Yeah.
And then, as long as you're not completely out of free space, then it could be a reasonable amount of time. But it's definitely not an undelete like the old FAT32 days where it was just like, yeah, in the file allocation table, we just overwrote the first character with an underscore to mark the file as deleted.
Yeah.
And, if the space hasn't been reused, then yeah, you can just put the file name back and have your file. It definitely doesn't work like that.
The complexity's ratcheted up quite a bit to be able to do that.
Well, mostly because in ZFS, you have this block pointer that tells you where the next piece of the file is. And as soon as you erase those, you don't know where any of the pieces of the file are, right? They're not written out like in FAT32 or something where they might all be in a nice row, especially if you're using RAIDZ or something. They're spread all over a bunch of drives. And it's really hard to go backwards. If you can rewind and find the copy of the block pointer that still pointed to those, then you can usually get things back. But it gets really complicated, especially if it's been more than a couple of seconds.
One of the things that's interesting to me is I think about this in terms of virtualization snapshots when you're using VMware or any of the other hypervisors. When you snapshot them, there is a disk pressure created because of the changes in the delta. So you can have some performance issues if you dozen snapshots on a VM. But ZFS works so much differently that you don't have the same performance degradation with snapshots. I think that's a nice feature as well. When you're snapshotting things on a disk, you can keep these points in time, but not lose as much performance.
Exactly. You don't lose any performance. The number of snapshots you have in ZFS has no impact on the regular read write performance. The only thing that's impacted is the amount of time it takes to list those snapshots.
Yeah.
If you go over about 2,000 snapshots, it starts to get slower because it has to break the table out into a tree. And so it takes a bit longer to walk the list. But yeah, because it, unlike bitmap based snapshot things like what VMware does and so on, you don't have to know, all right, this block we have two different copies of and so on. And there's no extra operations when you want to delete or kind of merge a snapshot and so on. Each snapshot is just a birth time and that, a couple of kilobytes of metadata. And the rest of the logic in ZFS saying, when I'm doing copy on write, I can't delete anything that's retained that's older than the snapshot because that snapshot will include it. If you overwrite a block that's newer than the newest snapshot, then we know we can go ahead and free it and it becomes free space that we can overwrite. But if it's older than the snapshot, it was part of the snapshot and we have to wait. And then once we delete that snapshot, we can easily figure out, okay, anything that doesn't exist now but is older than the snapshot is now free space. And it's very nice, but in particular, it has no performance impact on the speeding of reading and writing. Whereas like if you use the snapshot feature in LVM, the first snapshot takes half your performance and each snapshot after that
Yep.
halves it again. And suddenly you're getting terrible, terrible performance, especially for databases, and that's why ZFS can be so much more powerful because you can keep 1,000 snapshots and it has absolutely no impact on the read or write speed.
Yeah. I keep a lot of snapshots just because sometimes I make mistakes. And I've
Yeah.
been video editing, even my videoing stuff. You just keep frequent snapshots because I'm like, I've said I thought I deleted the right file when I'm building this. I now have to re-record B-roll, or I can roll back to my snapshot.
Yeah, the number of times that things have been saved by just having snapshots that happen every 10 minutes, just so that even if I only keep them for a couple of hours,
Yeah.
it means that when something goes wrong, if I notice quickly enough, I can go and undo it.
Yeah, the cost is so low in ZFS to do it. It's almost a why not do it. I encourage that. Of course, I have as you know, clients that didn't ask you to set it up come to you with problems you didn't expect. We did learn that their ZFS send, despite not having a lot of data, wasn't going properly, and it would take way much longer than it should for the amount of data change they had. So, logged into the system, I think they were in the neighborhood of 50,000 snapshots, and it was taking a long time to index the snapshots to send it because they learned they could start with recursive. They went and if there was something they could create a data set for, they did. And then
Mhm.
they checked the recursive button. And then they did all these, like, I want to do snapshots more frequently than probably was necessary. And we learned that when you do the ZFS send, it would get stuck just trying to index all the snapshots before it. Once the data got going, it would go. But
Yeah.
it's like, oh, that's what the pause is. That's so,
Yeah, and so the total number of snapshots in the pool doesn't ever hurt anything, but the snapshots per data set, as soon as they exceed about 2,000, it gets much more complicated. You have to switch from what's called a micro zap, which is just a straight key value pair, to a fat zap, which is a kind of pointer tree, and it'll scale infinitely, but it is a lot more expensive to find one specific snapshot.
yeah.
And also, by default, the way it lists the snapshot is sorting by their name and the creation time. But the creation time is metadata that's only stored in each snapshot. So when you're doing the list, it has to open all 50,000 snapshots and say, what's your time? Whereas if you sort by just the name, uh, that information exists in the parent dataset in a list, and it will make the list operation a lot faster. And we did some commits in 2.3 that increased the list of which columns you can use for listing and sorting without slowing down listing of a snapshot.
They had caused a UI problem in TrueNAS because when I went to list it, it just locked up right there. TrueNAS was not expecting to list that many. I had to go to the command line to figure out why. I'm like, why can't you list your snapshots? Went to the command line. Oh, that's why. That was an unexpected behavior.
Mhm.
Well, those edge cases. We're coming up at the top of the hour here. Is there any other parting ZFS advice, wisdom, or horror stories that we should share the last few minutes here with the audience?
If you're interested in horror stories, you should head over to our website and check out our Halloween webinar, which we told
Oh,
a bunch of
absolutely.
great horror stories that all have happy endings in the end. I think over the course of 2024, we covered just shy of 2 petabytes of data from people's systems where they had done something. Yeah, in most of the case, it was either hardware failure or somebody typoed a pool name or something and caused all kinds of havoc. Uh, we've seen HA systems cause more problems than they solve a lot of times, but we've continued to improve ZFS to make it be able to catch those things and make it more responsive to making sure. But the fact that ZFS is copy on write and we can kind of do that rewind thing of going back a couple transaction groups is most of the time what has saved everything. So
Yeah, there's so much
ZFS
good
is
stuff over it.
definitely copy on write.
Yeah, definitely copying what we said at the beginning, and there's so much good information I've referenced over the years at Klara Systems. So,
Mhm.
and it's just fun to read. The blogs you guys do, very deep technical write-ups that are wonderful if you want to learn. It's where I learned a big piece of them ZFS. If I post to my forums a lot, and you'll notice links back to Klara because I'm like, this is where I got this information from. Here's these people write the software, so are involved in much of it, so they certainly know it. They know it's actually copy on write.
Yes. But yeah, we've been helping various customers build features and do design and support for ZFS. So, like you said, if there's someone to build out a system and deploy it, and you need it to be able to meet certain criteria, then we can help you build it so it will. And yeah, we've worked on all kinds of features, including the one of our recent articles was about support for Linux containers, so that you can actually delegate one data set from your pool into like an LXD container so that root in that container can create their own sub data sets and snapshots and run Docker or whatever and have Docker use the ZFS driver natively and be able to do all this stuff to run their CI all within an unprivileged container. And, you know, customer one's container can't see the data sets from customer two.
That's awesome.
Yeah.
That's a really cool innovation right there. And with so much going to Docker delivery, that's a pretty common sense way to do it. A lot of
Yeah.
code, I'm sure, to make it work, but it in concept in my head going, that's really cool.
Well, that concept has been in ZFS since the beginning for Solaris zones. And when it was ported to FreeBSD, almost 20 years ago, that it's been there as well, but extending that to Linux, especially because namespaces work so much different than a zone or a jail, it was definitely interesting.
Yeah. Well, this has been awesome. I'll leave links over to Klara Systems and some of the articles we talked about. Definitely go check them out over there, and certainly check out the horror stories from Halloween. That's definitely lots of good information there dropped.
Yep.
Please contact Klara before you have a problem. Like when you think you're going to design, way better. It's save you some. It's actually less expensive to do it that way because telling them that that's not the right drive to buy or saving from disaster, it turns out those are much more expensive events.
Yep.
And limits your complexity. I run by people all the time whenever I'm designing stuff. I'm like, are you sure you want it to be this complex? Let's because the complexity, like you said, sometimes HA systems are often the cause of the drama that they were trying to solve.
They
So
cause more outages than they solve.
yeah, that tracks. This doesn't just apply to ZFS. Trust me, this applies
Mhm.
to people who come up with some of the weirdest way to do things. But hey, thanks for joining Allan Jude, and take care.
Yes, thanks for having me.